We are glad to see you tomorrow. I see that the deadline was very strict, but we are really happy that you come to us. So today I would like to introduce Sergey Kholkin. Sergey is research engineer in Skoltech, and he will tell you about practical part of Alexander Korotin lectures. Sergey, you're welcome.
Today there will be two seminars. So first will be a seminar on flow matching, complementing the yesterday's lecture on flow matching. And the second seminar will be connected to the second lecture. This is the seminar on flow matching. So what are we gonna do this seminar? First, we will try to implement the flow matching, understand how it works, and get to see some of its properties. We will take a look at two data setups, which is toy example and image generation example. And we'll take a look at flow matching with general transport plans, as Alexander was told, with independent plans, mini batch, optimal time. Can you see it better? Or do I have to enhance it more? Okay, first of all, let's start from some inputs and get to see the problem that we are going to solve as a toy problem. So that will be a problem of generating 8 Gaussian distributions from one Gaussian distribution. So you can see this 8 Gaussians, which are orange, which will be the target distribution that we want to fit our flow matching to, and the source distribution, which is just this one Gaussian that we will start our flow matching from. So, okay, this is just some toy problem. It's good to benchmark flow matching on. And so, yeah, let's recap some kind of theory. Maybe it is not forgotten from yesterday. Flow matching is a generative model, ordinary differential equation generative model that transports some arbitrary distribution to another arbitrary distribution by implementing a vector field and ordinary differential equations. So basically, you do construct a probability flow from some distribution which can be of arbitrary form of P0 to the arbitrary distribution P1. This probability flow will be defined as follows. So you have some kind of a vector field, which is finished. Well, I hope you see my mouse moving around the notebook. So this vector field, which will be have a dimensionality of RD times time to RD, where RD is our data, two-dimensional data in the toy case. And for the each point x0 that we will start our flow matching from, we will have this ordinary differential equation defined by this vector field V. And by inferring this ordinary differential equation, we can get a sample from the distribution P1. In practice, we can easily inference our ordinary differential equation by some kind of a numerical approximation solver, for example, Euler solver or some other more enhanced high-dimensional solvers like Kongekuta or Dopre. So, okay. So basically, the main problem of flow matching, what do we learn there, is this vector field. If we have a vector field, then everything is particularly easy. And another beautiful thing about flow matching is that it can transport from arbitrary distribution to another arbitrary distribution, in contrast to diffusion models, which can translate from noise to the data distribution, and not from arbitrary distribution to some arbitrary distribution. So, okay, this is great. How do we learn this vector field? How do we get it? So again, let's consider such distributions P0 and P1 that we want to translate from a distribution to another distribution, and some points from these distributions. So a point x0 from distribution P0 and point x1 from distribution P1. And so we do some kind of, we do sample random points from these two distributions and make linear interpolation between them. So this linear interpolation will look like that. So it's basically a line between x0 and x1, where x0 and x1 are sampled from distributions p0 and p1. And this interpolation actually defines as a sequence of distributions between distribution p0 and p1. And this sequence is numbered by some kind of a continuous time t. So, and then when we have some this PT sequence of distributions, we can learn flow matching to generate from these distributions altogether. How do we particularly do it? By just regressing this basically difference between x1 and x0. So this is like a beautiful thing about flow matching, because at the end, despite the generative model is relatively complex, at the end you just solve the regression problem, which is you just regress your vector field on the difference between some random points sampled from distributions p0 and p1. And yeah, you recover a vector field that translates from the arbitrary distribution P1. And in practice, we just implement this vector field as a neural network and just perform usual deep learning things to optimize our vector field to fit the regression problem. So yeah, we do just sample samples from one distribution, from our distribution, make a linear interpolation between them, sample some kind of random point in time t, and do this regression, solve this regression problem. So okay, great. Now let's particularly implement it. So first of all, let's take a look at our flow matching class. That will be like our main class for today. First of all, we of course do define a neural network. So this neural network works as some kind of a latent latent encoder-decoder style. So first we have this linear input that starts from kind of a input distribution, which will be our data. So in the toy case, it will be just two-dimensional real state space vector. And it translates it to hidden dim. So by the way, can someone say why do we have at the beginning not just the input dim, but input dim plus one? Yeah, because of the time step. Yes, yes, of course. So usually it is a bit more complex, because the time step is usually encoded using some kind of time encoding. But for the toy problem, we don't need particularly many expressive power. So without time encoding, it will do relatively okay. So we translate to some hidden dim by our input layer. Then we apply a sequence of residual blocks, which are, well, you can see this has some kind of MLP-based unit. So it inputs some kind of a hidden dim and outputs also hidden dim. You can stack this as many residual blocks as you want. And after residual blocks, we just have some kind of a decoder to the input dim once again. Yeah, of course, the device. So, okay, this is great. So forward is just a function that infers our neural network. This applies input layer, aka encoder, residual blocks, and decoder. And so, yeah, here we have, so for solving our regression problem, let's recap it once again. What do we need? Samples from P0, samples from P1, and linear interpolation, which is defined as follows. So okay, let's define linear interpolation. Call this function compute_xt because yeah, basically compute_xt. X well, x is basically x0 and y is basically x1. So we basically do some technical stuff with time, and yeah, we just like multiply x1 aka y by t and x0 aka x by 1 minus t, and that's it. That's it. That's very simple. And to compute the regression target, we just do x1 minus x0 or y minus x. So this is like very, very simple code. Like flow matching is actually very, very simple algorithm. Yeah. Okay. So next we want to sample from our learned flow matching. So yeah, remember that basically what do we learn here is a vector field of an ordinary differential equation. And how do we sample from ordinary how do we solve our ordinary differential equation numerically? Yeah, again, by like Euler solver, by some kind of numerical solvers like Euler, Runge-Kutta, or DOPI5 as here. So this is actually like if you work with ordinary differential equations on Torch, you are pretty much familiar, I think, with the library called TorchDin. Where is it? Yeah. So basically, this is a library that is made for ordinary differential equations on Torch, which is like highly efficient and provides many beautiful solvers for neural ODE, which you do not have to write yourself. And this solver is actually like pretty efficient. For example, this DOPRI5 solver, I believe it is like the state-of-the-art or nearly state-of-the-art solver for the ordinary differential equations. If you take into account like ordinary differential equations in generative modeling, for example, flow matching or diffusion models, then yeah, like many of these models do use DOPRI5 solver. And yeah, so okay, and here's some technical stuff, and we also want to plot trajectories to some kind to like debug our model mostly. Okay, now we have this CFA model class implemented. Now let's train some for matching. So first we will start from with for matching with independent transport plan. So yeah, so as Alexander said on the previous lecture, we can take flow matching with different general transport plans. So usually, like the simplest plan possible considered is the independent plan when you sample from distributions P0 and P1 independently. This is like some basic solution, and there are better solutions. But we would start from this like independent transport plan. And here is our training function. So it basically trains flow matching. It inputs some like flow matching class, a sampling function for sampling the pairs of data from distributions P0 and P1, and some deep learning stuff. Yeah, we just run some epochs, and what do we do to do one optimization step? We just sample points x0 and x1 using our sampling function. Just sample some t, which is uniformly distributed between 0 and 1. Compute our xt, which is again just the linear interpolation between x0 and x1, or like x and y here, with already sampled random time t. And we compute our regression target, which actually is independent of t, which is interesting. Yeah, so basically that's like all you need. Then you do some technical stuff to infer your neural network. Infer your neural network, get a prediction for a vector field, and then just optimize mean squared error loss. So like very, very simple algorithm. And yeah, that's like for training, that's it. So very, very simple. And yeah, so let's train flow matching. So while it trains, so the independent transport plan that we use here is not optimal transport plan, like in almost any sense. But it is good when you do not have some kind of a prior information on pairing from your data. So there exist many heuristics that try to some kind of think about some other transport plan that will leverage flow matching, which is better because basically with flow matching that you train depends on the transport plan. So different transport plan, if you use different transport plans between distributions X0, P0 and P1, the different flow matching you will get, like totally different. And yeah, I will actually show you it here because we will use two another data plans. It's constrained, yep. And let's see what has it learned. Sample some trajectories, and yeah, well, the thing about flow matching is that it is relatively fast on training because it is simulation free. But the inference is non-simulation free. You have to simulate an ordinary differential equation to sample from your model. So in many senses, this can be a bottleneck because like flow matching as a diffusion model, as our diffusion models is relatively time consuming and computationally consuming to sample from. And yeah, so we can see the star distribution, which is this green points, and the target distribution that has our flow matching has generated by these red points. So as you can see, this is like properly 8 Gaussians. So like flow matching learned our distribution very, very well. And yeah, so this is great. But then let us see the trajectories. So the trajectories here are the interesting thing because as you can see, they're not straight. So for example, like take this into consideration. Yeah, this is not particularly straight trajectory. Or this one, so this one's. So some of the trajectories are like almost straight, like this one, for example. Or I don't know, this one. But many trajectories are not straight. Why are not straight trajectories are a problem? Because so if you have straight trajectory of your ordinary differential equation, then ultimately you can sample from this ordinary differential equation. You can numerically solve it by just one step. So if we have, so basically the lower the curvature of your ODE, the lower the computational error of solving this ODE numerically. And basically that means that you have to apply your neural network less, and this saves like computational resources and time. So like non-straight trajectories are bad, they require more computation, and straight trajectories are good, they require less computation and less time, which is like great. And flow matching, you always want something that is very similar to straight trajectories. Yeah, and we will work with straight trajectories further. We will take a look at straight trajectories today. And another interesting thing here is loss, because
so basically, in a sense, we would like to have straight trajectories, right? In order to do it in as little step as possible, but at the same time, if we just build straight lines, they're not good, and we need
they're not what?
They're not good. Like
why they're not good?
I mean, the entire idea of this rectified something, I don't remember how it's called. is to find straight trajectory, but the straight trajectory that works. But we start with straight trajectory, but the one that we start with, this one is not good. But we make we learn this this new networks in order to learn the straight trajectory. But we start from straight trajectory. This is something I don't understand.
Yeah, okay. So you mean by straight trajectory, like this one, yeah?
Yes, we start with it, but at the same time, in the end of rectified something, we also end up with straight trajectory. But these are not good. This is not.
Yeah, so you see, this is not a ordinary differential equation trajectory. This is just a linear interpolation that we take given some points x0 and x1. If we could just like turn this into an if we could find such a vector field that produces such straight trajectories and generates x0 and x1 from our distribution p0 and p1, that would be like great. But this is not an ODE trajectory. So you cannot like start from x0 and infer this trajectory because you do not have x1. So that's basically the problem. You got to have x1. And this is like not inferable at the moment. So there is a way to get, to let's say, learn almost this thing and yeah, get straight lines, which will look like that. But like x1s, x0 and x1s must be from some particular distribution, which is the optimal transport plan, which is actually hard to get. So yeah, like to some kind of wrap it up, you cannot use this at the inference stage because you don't have x1. And if you could learn it, that would be great, but it is actually pretty hard to learn it. Like this x1, which will give like this straight trajectory.
Okay.
Have it been? Yeah, so I have just like shown a bit of straight trajectories, but yeah, let's take a look at loss because yeah, as you may remember, this is our loss, and this is just a regression loss, and hence it is always greater than 0 because it is basically a math expectation of L2 norm. So it has to be greater than 0. But what is the interesting thing, because maybe like in many cases, you are used to the fact that, well, the optimal loss should be like near 0. And here you see that loss has converged and it is not 0. It is like somewhere like 3. And actually, this may be almost optimal value for this regression problem. Why? Because the optimal value of this regression problem doesn't have to be 0. Like in general, it is greater than 0. So value of loss is not 0, but we're actually almost near the optimum here. And the interesting thing that the only case where this loss, like our regression loss, yeah, comes to 0 is when this x0 and x1 are sampled from optimal transport plan distribution. And yeah, I will show it a bit later. So yeah, this is like the loss is near the optimum, but the optimum is greater than 0. And yeah, trajectories are not straight. Let's find some way to get them straighter. So first, we will introduce an optimal transport mini-batch plan. So yeah, so Alexander said we can use flow matching with different transport plans as an input. So basically consider some samples from P0, some samples from P1, and that you want to construct some kind of this distribution P, a joint distribution, which is, well, has some properties. And you sample like X and Y's from this distribution. So this distribution can be independent, as I showed earlier, but also it can be, well, actually the best distribution for the flow matching, this distribution P, is optimal transport distribution. When you legitimately sample from distribution P0 and P1, but the difference in terms of L2 norm between your x0 and x1 is minimal. So it's some kind of a minimal energy transport plan. And yeah, and this is great, but it is hard to get optimal transport plan. And what do we usually do is get an approximation of this optimal transport plan. So we sample some endpoints from P0, some endpoints from P1, and we cast a optimal transport problem, not between general measures P0 and P1, but between the samples P0 and P1. And optimal transport between samples, so basically the distribution would be just a mixture of delta functions. In that sense, the optimal transport plan is really easily solvable. But it can be converted to a linear optimization problem, which is solved, like I believe, in cubic time in the number of samples, something like that. And yeah, so you can, if your batch is not that big, you can actually solve this problem of optimal transport on some kind of a mini batch and use the transport plan that you get on the training of your flow matching. And this would be better than independent plan, but it requires some computation. So yeah, let's see how to implement this. So we would use here a beautiful library called POT. This is like very famous library for Python on optimal transport. If you like familiar with optimal transport, you surely know what it is. So it's basically state of the art for PyTorch and optimal transport. And yeah, so we do here some technical stuff, and basically we do take some samples x0 and x1. We construct matrices of distances between x0s and x1s and pass them into this OTFN, which is which solves the linear optimization problem and solves the gets optimal pairing for each x0 to the x1 from your samples distribution that you like pass here as a function argument. Okay, all right. Then there's just some technical stuff. And yeah, this is also like called the discrete optimal transport because this is basically solves the optimal transport between the mixture of delta measures or some samples, not the general continuous distributions, which is harder in general than discrete one. All right, so we do basically implement the sample, which is very similar to the independent one that we've implemented earlier. And yeah, so like another thing that we do here is I've said that constructing this mini batch optimal transport plan is like requires like I think cubic time in terms of number of samples, and hence it like if your batch is very big, then you have to do a lot of computation. So what else can we do here is to divide like our already mini batch by some mini batches and solve optimal transport between these mini batches, construct from them one mini batch, and then pass it to the our flow matching. So this makes the algorithm faster. So okay, let's train it. So again, the only thing that we change here compared to the previous independent plan flow matching is just the way we sample points x0s and x1s from our P0 and P1 distribution. So like we only like in terms of formulas, like the only thing that will change here is like this particular math expectation. Now it is like you sample independent points from P0 and P1, and now you will just sample these points from some kind of an approximation of transport plan between P0 and P1. So also you can construct some other interesting plans here, but yeah, there are papers on that, and basically the optimal transport plan is the best one. Yeah, also, as you can see, the training of previous flow matching taken like 1 minute, and training of this flow matching takes 2 minutes. Why? Because solving mini-batch optimal transport costs some computations. That's why it is 2 times more costlier in terms of compute. No, not costly in terms of compute, but takes too much time. Yeah, so this is you do get let's say better better properties of your flow matching by paying some kind of a computational cost on top, some kind of this trade-off between quality and computation. Yeah, like better in the micro.
So is this mini batch flow matching is something that's related to Kantarovich optimal transport, where we transport a distribution to distribution?
Two formulations of your optimal transport, one of which considers only the continuous measures. I don't remember like which one, Monjo or Kantarovich, and the other that can also consider like mixture of deltas. And yeah, like this is basically solving one particular instance of optimal transport that is between two distributions that are a mixture of delta functions. So basically.
And before that, we used the point-to-point optimal transport.
Well, transport between delta measures, yes.
So this is exactly the practical algorithm to do distribution to distribution.
Well, yeah, well, given some samples, you can pair. So you have like x0, and you can pair another x1 from the distribution that you already have with like which is like closer to the x0 in some kind of cost function, for example, L2 norm. But like this cannot generate you samples. So if you have like two sets of samples, then you can make some kind of a pairing between them, but you cannot generate samples that way. So.
Okay, thank you.
It has trained. And yeah, you can see that trajectories are actually a lot straighter. Like some trajectories, like these ones, like almost all the trajectories are almost entirely straight. Like there are some that are not straight, like for example, this one. But this is because we use the approximation of optimal transport, not the optimal transport like itself. And yeah, it learns the distribution pretty well. And so yeah, these trajectories will be easier to infer than the previous ones. Let me recap the previous ones. Yeah, so actually another thing that these trajectories are longer. These trajectories are longer than the optimal transport ones, and these are more curvy. So like in generally, this is harder to inference. It gives more numerical error during the inference than the optimal transport ones. And another thing is like training loss. Because, yeah, so previously we have seen that the optimal value for the training loss is somewhere like around 3. And here it is like 0.25. Like actually, yeah, I already said that the only case where optimal value of loss function for this flow matching would be 0 is optimal transport one. And so it is relatively close to 0. And it means that we get like relatively good approximation for the optimal transport if the loss is near 0. Yeah, so this can be some kind of like marker of optimal transport. And yeah, well, this is like pretty cool. Another interesting thing, what will happen if we consider negative evil optimal transport? So we will take anti-optimal transport. So if we optimal transport basically tries to find the pairs of samples from x0 and x1 that are minimal in terms of the like energy spent for translation or the L2 norm between them. And here we will try to not minimize the L2 norm, but we maximize it. So we will try to pair the points from the different parts of distributions. For example, like for this point, we would map like, for example, this point, which is like the farthest point away. And for these points, we will map these points, which are, again, far away. Yeah, let's see what will it get us. Yeah, again, it's like tuning string. Yeah, but okay, I will like a bit omit this training and we will take a look at results. Yeah, so from the first point of view, these trajectories may seem straight. However, they actually have this sharp edge. So basically, like if you start from this trajectory, you go to the center and then you basically turn around. Yeah, very, very strange trajectory. And yeah, again, the inference of this trajectory will actually take like a lot of time and a lot of compute because you have to approximate it well, you have to find this change point. And to find it, you have to like approximate your trajectory very well. So this is like what you do not want to see in your flow matching. So this will take like a lot of compute for inference, and yeah, like the pairs that you get are like not very good, and yeah, like actually loss is like lower than the independent transport plan that we have considered first. Yeah, but the independent transport plan is better than this one because the independent transport plan trajectories, they are, well, they are a little bit curvy, but like these are much more complex trajectories with well, they're just bad. Curvy trajectory is better than something like this. Yeah, so okay, so for now we have seen three different transport plans: independent, mini-batch, and mini-batch and anti-mini-batch optimal transport. So the independent is okay. The mini-batch optimal transport is a bit better, but you throw more compute. And the anti-mini-batch is the thing that you do not want to do ever in your flow matching. And so, yeah, as I've already said, the mini-batch optimal transport is one of the ways to help to make your trajectory straighter. And there is another way to make your trajectory straighter, which is called the rectified flow. So what it is not particularly a flow matching. This can be considered as some kind of an iterative flow matching. So you do train one model, one flow matching model, and then you do train another flow matching model on top your already trained flow matching model. So basically, before that, how have you trained your flow matching? By optimizing this loss, yes? And you had this like distribution here, x0 and x1. And now this distribution just substitutes from the distribution of generation from already trained flow matching. So you do take, like, for example, some x0 from your like distribution that you can sample from, infer your flow matching, get x1 given x0, which is like important. Yeah, and train your flow matching on that pairs. So it would be like another pairing that is alternative to mini-batch optimal transport and anti-mini-batch optimal transport and an independent one. Why do we need it at all? Why do we need it at all? Because actually it is known that let's say if you consider a sequence of flow matchings that are trained using previous flow matchings as a transport plan, then it is known that with each flow matching, your trajectories get straighter. So yeah, this can be like more rigorously formulated as that. As I've said that basically the straightening of trajectories is equal to minimizing some kind of a quadratic cost function between your samples from x0 and x1. So if you have like samples x0 from one distribution and you want to minimize some kind of quadratic cost of transporting to the distribution P1, then minimizing of this quadratic cost is equal to like basically it's the task of finding the shorter path to the distribution P1. And the shorter path in L2 geometry is what? It's a line. It's just a line, just like we use for the like starting interpolation right here. So yeah, at the end, if we do perform our flow matching very times like one flow matching on top of another flow matching, we will get like in particular this like straight trajectory. Okay, so but what is the problem here? What is the problem here? Yeah, what is the problem here is that every time, so like flow matchings that you learn are not ideal. They do have some kind of accumulative error. So they do not like minimize this flow matching clause to the full. They minimize this flow matching clause up to some like with some approximation error. And if you stack some flow matchings on top, then the previous flow matching gives with already it already has some approximation error. Then it translates this approximation error to the second flow matching, and the second flow matching is also learned with approximation error. And so you do stack this approximation error on top of each other, and at the end you can accumulate a lot of error. And basically, what this error translates to is that you generate not the distribution that you want to. So you want to start from distribution P0 and end at distribution P1. And if you accumulate many accumulation error, then you can start from distribution P0 and end at like some shift distribution P1. That will be like not this one, but something lower, for example. And yeah, this is like the price that you have to pay for the reflow procedure and rectified flow matching. But sometimes it is worth it. It is worth it because in practice, you usually do like one or two flow matchings on top of each other. So yeah, let's say like maximum you train one flow matching on real data sample from your data distributions. Then you use this flow matching to sample another data set, train a new flow matching component, and then like use the second flow matching to generate some data and train like the third flow matching on top of the second, and that's it. So after that, you do not. All you do is accumulate error, and your trajectories in practice do not get any straighter. So yeah, that's like the good thing. And another problem of this rectified flow is that the training procedure is not simulation free now. Yeah, like can someone, for example, say why our training procedure is not simulation free now?
Is it because the output data is the result of simulation for the next iteration of rectified flow?
Yeah, you have to simulate your previous flow matching to generate the data, exactly. And that's why like it takes a lot of compute to actually perform this rectified flow procedure. Yeah. So okay, let's implement it. And yeah, like this is actually like a big problem in practice, because like if you train like big models in like industrial scale, then like the inference of your models is actually way costly, and yeah, it takes like a lot of compute. So yeah, let's construct yeah, a way to construct a new data set for us. What do we want to do here is to sample from distribution P0 and infer your previous matching on the given samples from distribution P0. Yeah, so this pair of samples would construct our new dataset. And then what do we want here is to construct this kind of a new dataset. Yeah, and you can see that it takes some time, like 1.5 minutes. So the first flow matching was trained faster than we generate dataset for training Actified Flow. So yeah, Actified Flow is quite expensive. Yeah. Yeah, and that's here to like show the performance of state trajectory straightening is the use for our base model is this flow matching anti-mini batch model. So this will be like this model. So as you can see, it has not straight trajectories at all. And yeah, like the goal of rectified flow and like flow procedure is to straighten the trajectories of already given flow matching. So we can see if flow matching, if rectified flow succeeds, if it like translates these trajectories to the straighter ones. Yeah, like
I have a question about simulated data. How can we know that the new sample data from P1 is actually from P1? Like we have ground truth data, like we have pairs mappings from x0 to x1, they're ground truth. Then we train it first time, then we sample new x0s. Oh, okay, we know P0, we follow the flow, then we have some point x1. How can we know that it's not even close to distribution, that it's not the gibberish completely?
Yeah, so we don't know. The only way then like you can ensure this is that you train your first matching good. So the base of this reflow procedure, this rectified flow procedure, has to be good. It should not generate gibberish because like yeah, the error will accumulate, and the second flow matching that you will train upon it will generate even more gibberish you have like in the first place. So you like it is very important to make sure that you actually generate something like maximally possibly close to the actual data distribution. Otherwise, it will like shift for a lot.
So we have like trajectories from x0s to ground truth points. So they are true. We learned it good. But how can we say that this distribution has no spots, empty spots, and near the x1 point, there is no more points that are from this distribution? How can we say that we haven't got to this blind spot or something?
How do we ensure that we have no blind spots in our generated distribution?
Yeah, like we follow this flow. It simulates our ground truth perfectly. We trained it good. And how can we guarantee that following this ODE, but from another points from P0, we will go to correct distribution.
Yeah, like again, no. Like the only thing you can do is train your flow matching, first flow matching pretty well and measure some kind of metrics that do answer this question. But like in general, there is no good way to, well, there is no like, let's say, fully theoretically, like fully justified, like very good way to actually do this. You just use some kind of heuristics and hope that everything is okay. Like in practice it works. In practice it works. So yeah, like of course, because you actually have some maybe like blind spots in your distribution or some shifts of your distribution, and that results in bad rectified flow. Yes. So and this is like pretty common problem as far as I understand. So yeah, like the best thing you can do is you validate your first flow matching very well and make sure that it's like as accurate as possible.
Okay, thank you.
It has already trained, and as you can see, actually, the training took like less time than generation of data. Yeah. And so let's start sample format. It takes a lot of time to sample. Yeah. So you can see that these trajectories are the ones that we had with optimal transport mini batch plan. Because apparently mini batch optimal transport plan is a worse approximation of optimal transport than this rectified flow procedure gives. And yeah, so these trajectories are very, very nice. They are very easy to infer. You can like take a look at these trajectories. Most likely you can most likely this is like almost everywhere is a straight line, and you can infer your ordinary differential equation by just having one step. So this is great. Another thing that says that it is optimal transport is this loss, because like it is almost zero, and it has almost, well, it has some variance, but the variance is very low. This is like the state signal that it is very, very close to the optimal transport. So if we consider, for example, like our mini batch optimal transport, you can see that it produces a lot more variance, and in general, the optimal value of loss is higher. That means that it is worse optimal transport than the rectified flow one. And if it is an optimal transport, then it has straight trajectories, and this one has straight trajectories, while the mini batch one has some non-particular straight trajectories. Yeah, like this ones. And remember that we have started like our reflow procedure straightening our trajectories from this one, which has a lot of variance and loss. The optimal value is far greater than 0, and the trajectories are not straight like at all. So yeah, so in that sense, this rectified flow procedure is a success. It is like very good, performs some miracles, but again, it is non-simulation free. It can acquire some like distribution shifts, say approximation errors, and it is it is costly. So so again, this is some kind of trade-off between quality and computation. Yeah, and let's take a look at all our flow matching that we learned so far. So again, this is the independent one. You can see the trajectories are not straight very much, but this is like the less computationally demanding experiment that we had so far. Mini batch one, which falls a bit of a computation on top, but the trajectories are straighter than the independent ones. So this is like relatively good. And like these trajectories are not straight because, and you cannot like surely infer them using just one step of Euler solver for your ordinary differential equation. but like it is relatively good. It is relatively good. You certainly do need less steps of numerical solver to solve ordinary differential equation resulting from mini-batch plan than from independent one. Like that's for sure. And in practice, that will like save a lot of computational resources for you. Yeah, but again, you will spend more computational resources on doing this mini-batch optimal transport thing. Like anti-mini batches optimal transport is the thing that you do not want to get because trajectories it will take like a lot of steps of ODE solver to solve this trajectory like the right way and without approximation error. And yeah, so this will take a lot of compute in practice to inference. And the certified flow has like almost straight trajectories. The transport plan is almost optimal. It has like straight trajectories and like I think it almost can be inferred using just one step of ODE solver, which is like great because the complexity of this thing is like the complexity of GAN, which are very, very fast. Yeah, and I think that it is like relatively hard to get such straight trajectories for the diffusion that you can just sample in one step of diffusion. But you can like do it with flow matching under some circumstances. So yeah, this is great. This is like part one. So this was a toy problem. This was a toy problem, and yeah. So maybe some kind of questions related to the first part.
Might be a silly question, but how do we know which point corresponds to another point in two distributions? I mean, why do we have exactly this mapping of point to point?
Decide on which mapping of points? Like flow matching one or optimal transport one or like?
For example, optimal transport one.
Yeah, because if you train your flow matching on optimal transport plan, then your trajectories will be straight.
They are straight, but if we're matching distributions, how do points correspond to one another? I mean, how do we transpose them to one another here?
You mean what is the relation between points like the parts of ODE trajectory?
Yes, yes.
Well, yeah, again, this would be, so this flow matching would be a way to construct the is an optimal transport plan between one distribution and another distribution. That means that if we start from one distribution, which should be this Gaussian sample point from it, then the flow matching would give us the another point from this like red 8 Gaussians distribution that will be the closest one to the already point that we have. But it would like also, you would also need to fit all the 8 Gaussians. So it cannot be like exactly this point that you started from, because this point is not from like 8 Gaussians distribution. So you would have to like some kind of solve optimization problem and see. So for example, if you start from this point, like which is the closest point to it from the 8 Gaussians, like point from this Gaussian. If you start from like this point, which is the closest point from the red distribution, like some kind of point from this Gaussian, etc. Not from this Gaussian. So you will, if you have like optimal transport plan, you will not go from here to here, but you will go from here to the closest Gaussian.
Okay. And we are plotting the result of the inference of the
simulation. Yeah. This red are like sampled points from flow matching.
And the green ones?
This from basic start distribution. They just from noise distribution. They're not sampled using flow matching. They're sampled like from Gaussian distribution.
Okay, thank you.
Okay. Then let's go to the second part, which would be image-to-image generation problem. This is like a little bit more serious problem. We will try to generate samples from Carl Smith's dataset in 16 by 16 resolution. So we have this dataset here. So yeah, basically we do some standard stuff by transforming like to tensor, to resizing, and we do random coloring of our MNIST dataset into 1, 2, 3, 4, 6 colors. 6 colors. And we choose not the full MNIST dataset, but the part of MNIST datasets regarding to some digit. Like, for example, I think in our case, it would be target digit free. So we will have part of MNIST datasets with 3 digits, and we will color them in like 6 colors. So let's take a look at our samples from our distribution. We would have like 5,000 or 6,000 of images in our data set. Let's plot them. So this ones, yeah, you can see it's like colored color digit of 3. Yeah, so for matching, we must have 2 distributions, one from we start from and the other we go to, and we want that we start from would be a noise distribution, just a noise distribution. So like in particular, I think it is just, yeah, it's just torch random. So you generate like each pixel independently from normal distribution. Okay, so here neural network would be a bit more complex. So here we do actually need a time encoding, which is like usually positional encoding plus like some MLP on top. And here we import the neural network from the diffusers library, which is like actually pretty good. So this UNet 2D model from diffusers library is yeah, it is pretty good. And if you want some kind of a baseline solution for your like say diffusion model, flow matching, like bridge matching that we'll talk about today, then it is like pretty good solution to take this UNet 2D model from diffusers. If you like more hip and cool and want some kind of a more powerful neural network, then you can take like diffusion transformer, which I think is also present in diffusers library. So yeah, check out diffusers, very good in terms of neural networks, and you can like very easily just import and everything will be all right. So yeah, we adapt our like UNet 2D model for 32 by 32. Yeah, seems like the digits will be not 16 by 16 by 32 by 32. Okay, all right. Yeah, and then if we have already associated our neural network, which is like, again, UNet neural network, then we do the same thing. So forward, we just infer our neural network. In Compute-XT, we just, again, compute this linear interpolation that we have like implemented in the first for the toy problem, which again is just linear interpolation. And then as a target for our regression, we just take like the difference of x0 and x1 or x and y. Like sampling is done like the same way as previously by using torch-din library. With again Dopre 5 solver, because this is a very good solver. Okay, so yeah, so here I have some, yeah, so again, the training procedure is like the same, but we add some deep learning techniques to make our like optimization a bit nicer. Like some scheduler, but I don't think that is actually, yeah, it's commented. Gradient clipping, etc. So, but other than that, you just sample from your data independently in that case, and sample some time from uniformly from 0 to 1 intersection, and XC, which is like linear interpolation, and regression target. Infer your neural network, perform your regression. Everything is great. So yeah, we can, well, we can train the neural network. However, it trains like for 7 minutes, and load already trained one. It's training function. And let's take a look at some samples from already trained model. So again, we start from the noise distribution and end at the colored digits of freeze distribution. So this is that we started from, and this what we learned, and this is like the target. So as you can see, the learned freeze are relatively close to the ground truth ones. Well, they have some kind of an artifacts like this strange thing, and this is like more like 9, not 3. But overall, like for such a toy case, this is like relatively good. They all have distinct colors, and yeah, well, this is like okay. This is like okay, and so yeah, as you can see, flow matching is also great on like real problems, real image generation problems, and well, I believe that's it. So to recap what we have done here.
It seems like the model is doing well in determining the shape of the target distribution, but not the color. Could you comment why? Excuse me, is like the mic seemed to be not working.
Yeah, so what do you mean? Like the color is not accurate? Yeah, well, I mean, it seems like a little bit of a linear shift. Yeah, like, I think, yeah, so as you can see, like actually there are really 3 colors. Well, there are like some different colors here, and as you can see, like you have this lime green 3 and this like, you know, toothpaste color green 3. So like 2 different shades of green. And also you have this like yellow. So like for matching also like it is not entirely accurate, and it also learns like some colors that are in the middle. So if you train your model more, then it would generate like more accurate colors. But like in the middle, it can generate colors that are not like entirely accurate, and something in the middle, like between this one, and this one, or maybe like even blue one because it's like not far away. In that sense, well, yeah, there are some color inaccurates, but it will like go if we will like take a bigger neural network and train our model for like more. Just if we will just spend more compute on our model, it will get better. So a little bit of recap what we have done in this seminar. So first, we have started from some kind of theoretical recap of how much flow matching works. Then we have implemented our flow matching on this toy Gaussian to 8 Gaussians problem, visited 3 versions, yeah, 3 versions of just flow matching. Like let me scroll to it. 3 versions of flow matching, which is independent one, which is like okay, but you can get better. A mini batch one, which requires more compute, but is a bit better. Anti-mini batch is that thing that you do not want to get in your life. And the anti-mini batch plus reflow that also like requires more compute, but is very, very good. Then we have implemented our matching on the image to image on image generation problem, and yeah, it works like relatively good. So yeah, I think that's it. So
dear colleagues, now you will have an opportunity to ask your questions. You can do it as from online as from offline. Dear offline colleagues, yeah. Microphone, please, here.
Thank you for the seminar. I have a question. For me, it's counterintuitively that mini batch solution trajectories are straighter than usual batch, because from classical machine learning, if you have a bigger batch size, the direction of the optimization is smoother and like more concrete.
Does it work? It does work. Okay. Yeah. So the thing that so first of all, actually, the size of batch is like equivalent in independent one and mini batch one. Yeah, like it is called mini batch because we call like we always call batches like mini batches. In that sense, like this mini batch and this mini batch. But in this mini batch, we also do solve an optimal transfer problem between samples to get some kind of an optimal pairing between them. And like the thing, why do we get a straight trajectories here is because we solve an additional optimization problem. We so like imagine like independently sampled points from, okay, let's take like from this one. So for example, you can take a sample from this red distribution that will lay in this Gaussian, and then you take some independent sample from your Gaussian distribution. It can be from any point of your Gaussian distribution, for example, from this part, which is like far away. And you can guess that taking samples that are far away is not particularly good, especially for flow matching, because the flow matching that you learn is particularly dependent on the pairs that you pass into him. Like even not in terms of the optimization, like the niceness of optimization problem you get, like smoothness of it, like etc. But in terms of like actual minimum of your vector field is different when you push with different transport plans into it. So in that sense, if you take again point from this Gaussian and take a point that is much closer to it, for example, like from this area, your path would be shorter, and it would be a lot nicer to optimize over this kind of pairs than like pairs from like different parts of distributions.
Okay, I see. I understand now. Thank you.
Yeah.
Yeah, thank you. Can you please tell if this mapping is one-to-one or not?
So this is a tricky question, like which particular mapping?
I mean, if we train flow matching from one distribution to another?
You mean reflow, like this one?
Yes.
Is it one-to-one?
Yes.
Yeah, so in general, flow matching is one-to-one mapping, like in general, because you have like flow matching is basically ordinary differential equation, and ordinary differential equation is like deterministic. So you start from one deterministic point, then you end up some another deterministic point, which is like, this is different to the like diffusion models that do have stochasticity in generation. Like flow matching does not. So basically it is one-to-one mapping. Yeah, like.
Okay, and why the this generation stuff with noise is not one-to-one then? Like the very last slides where you showed
like the image one you.
Yes.
Not one-to-one? Like, what do you mean?
Or is it one-to-one? So can we recover?
No, it's still one-to-one. So you get some kind of a sample from noise distribution, and like flow matching gives you some corresponding mapping to some like, some digit of free. Of your like noise distribution, you do get different digits of free.
Okay, and also, do you have the initial correspondence between target domain and the initial domain, like in just data set, or do you have some algorithm to decide what points should correspond to what points in the like training data set?
Yeah, so you mean some of a pairing between the starting distribution and ending. Like in theory for flow matching, again, you can do it because we had like this optimal transport plan, like different pairing between data in terms of like toy flow matching. However, like with in practice with flow matching, there is thing, because flow matching is, well, theoretically, you can do it from one arbitrary distribution to another arbitrary distribution. In that sense, yes. Like in practice, flow matching is almost always trained with some noise distribution and some data distribution. In that sense, your pairing is like constrained by this setup. And I believe the best thing you can do is make some kind of a mini batch optimal transport or some heuristics like this. It's, yeah, maybe if you have some kind of another way to make some pairings between noise and data distribution, yeah, you can do it. Like if you have two distributions that do have some kind of a pairing, for example, like clean image and corrupted image, in that sense, yes, you have like this pairing and you can learn flow matching on this pairing. Yes, you can. But like in practice, it would work not very good because flow matching is deterministic.
Yeah, because it seems like there could be intersections of trajectories, and it will lead to non-one-to-one mapping.
Yeah, like I mean, there would be some intersection of trajectories in the like starting distribution, but that's like okay. Well, you do not want intersection of trajectories. Well, we'll say that it is better to get rid of intersection of trajectories than have intersection of trajectories. Yeah, that is true, but you can still live with intersection of trajectories in your initial data, and it would be like not the best solution, but it would work.
And what's the bad thing about intersecting trajectories? How can we distinguish them? What are the properties?
Because let's take a look at veloc. Let's take a look at veloc. So imagine, here it is. So imagine you have some intersecting trajectories. It means that for some xt, you would have two corresponding to it x1s. Yeah, and like it would give additional variance to this loss. While if your trajectories do not intersect and you have for one xt, one x1, then you would have lower variance. And actually that would be like optimal transport plan, straight trajectories, and your loss would be like minimized to the 0. But yeah, like basically this like variance here, it is because you have intersection trajectories in your data. If you do not have them, you would have something like this or this with very low loss without variance. So basically intersection gives variance.
Okay, thank you.
Okay, thank you for your seminar. I've got a question. So suppose that we trained our model and it's pretty huge. It has a lot of parameters. And now we want to employ a rectify flow procedure. So the question is, for example, can we initialize a new model with the weights of previous one and just fine tune it? And for example, spend less time on compute? Or it is a bad practice here, maybe approach.
Yeah, so if you would take like yeah, this is like a common procedure for like deep learning. Like imagine you have you are doing this rectified flow procedure and you start from like 0, like random noise initialized weights, and you would have to train your model like a lot. And like considering the fact that to train your model from scratch, you would need a lot of data that would need to be sampled from already given flow matching, like it is enormous compute that would be spent on it. So basically this, like when you do a flow procedure, it is more of a like fine tuning rather than really training a new model. If it would be like training a new model, it wouldn't be computationally feasible and nobody would do it. So yeah, just initialize your like new model with weights of previous, and it's like more like fine tuning.
Yeah. Okay. Thank you.
Yeah, thank you for the attention. Yeah.